So metamorphic facies mapping in field. This is a practical approach. It is very much interesting, especially from exploration point of view. This video is going to be interesting and very important. As you have might have observed or noticed that there are certain places where different metamorphic grade or the metamorphic facies assemblage occur together. Suddenly one grade are interlying along with others, but which is very much unusual. And how does it happen? What is the reason behind getting these kinds of intimate association at certain places, especially fold and thrust belts, especially for example uh, in African continent, Tanzania, where Tanga graphite deposits observed. Their graphitic cysts are of relatively lower grade rocks, where graphite is found in green cyst to amphibolite grade. Immediately at places garnet rich higher amphibolite to granulite rocks, mafic granulites, they are coexisting almost together. How is it possible? So that thing I am going to discuss here. First, you see a map of different area. Here you can understand how they are coexisting. You see the scale first. This is a 50 kilometer, this area. So it is very much reasonable, no problem in that. This is basement province, and now as you see, chlorite, biotite, garnet, andesite, sillimanite, the metamorphic grade is increasing from northeast towards southwest. Grade is increasing. Okay, so this is quite reasonable. So that means this direction is indicative of deeper part of the crust. Okay, because chlorite in metamorphic domain indicate for regional metamorphism indicate around 200 degree to 300 degree Celsius. Biotite above 400. Of course, chlorite biotite can be coexisting. I should not repeat these basic concepts of metamorphic index minerals. That is called first appearance, not last appearance. That means when biotite zone starts based on biotite index mineral, chlorite also can coexist. Even when garnet zone starts, garnet will appear fast, but biotite can continue, chlorite can continue. Okay, so with this, let's proceed. How is it possible? See, simple thing, let me show you how the basic concepts of grade. Because of geothermal gradient, this is normal geothermal gradient. Okay, because of geothermal gradient, pressure temperature condition increases, and due to changing stability field from chlorite, then biotite, garnet, and so on. This way, in undisturbed terrain, zone can be specified. But when some folding or thrusting occur, usually in fold and thrust belts, mobile belts, these things happen. What it will be consequences for this? They will be juxtaposed often. Okay, so that is the reason suddenly all of a sudden they can also coexist. That is not an ordinary circumstances. Different reasons are there behind this. Okay, so I hope you must be knowing the metamorphic facies, and exclusively I have discussed earlier as well. So general characters of major three common facies. See, metamorphic facies diagram, you might have seen so many facies: low grade metamorphic facies, high grade, moderate grade. But in general, for regional metamorphism or contact metamorphic facies, of course, but for regional generalized metamorphic facies, green cyst, amphibolite, and granulite are of most significance, because that is most commonly encountered rock types in practical geological exploration related terrain, like graphite or granulite, graphite in low grade green cyst to amphibolite, or granulite terrain often, so garnet, as I have told earlier. So graphite can occur in within this three range, but mostly confined in green cyst to amphibolite. By the time granulite by reach, graphite gradually content is reduced. Okay, so granicist phases occur in 5 to 15 kilometer for normal geothermal gradient portion. It can varies. All the pressure temperature condition as well as depth may vary. Amphibolite ranges from 10 to 30 kilometers and more than 35 kilometers. Granulite usually starts, but that depends because there are three characteristics: pressure, temperature, and fluid. All the three parameters control the things. So the occurrence of graphite in granulite, amphibolite, and greenschist facies rocks is governed by, see here, for basic things, as you must be knowing, where greenschist, amphibolite, and granulite forms, what are the key minerals. But graphite usually, as I have told, greenschist, amphibolite, and very rarely in granulite terrain. Okay. Now, how granulite, amphibolite, and greenschist facies rocks may occur in close proximity? As I have told, that zone is specified where this is 5 to 15 kilometer, then 10 to 30 kilometer, and granulite is 35 kilometer, more than 35 kilometer. So it is a widely specified occurrence for getting graphite, granulite, amphibolite, greenschist. So whenever we are getting it, these three in close proximity, that certainly indicates something unusual. Okay, so what are the major factors which can make this? First one is structural complexity and tectonic activity. Mostly, as I have told, major folds, faults can juxtapose rocks of different metamorphic grades. Mostly thrust. What does thrust do? Actually, deep crustal levels they brought up and in contact with low-grade amphibolite or greenschist facies rocks. Similarly, in case of normal fault as well, they can expose deeper granulite facies rocks adjacent to greenschist facies rocks through crustal extension. Similarly, like shearing, also shear zone. Other than that, metamorphic overprints like retrogression, often it happen. Higher grade rocks like granulite can be retrogressed to amphibolite or greenschist facies due to later hydration or cooling events. But that time it will not be occurring together throughout. So patchy occurrence will be taking place because retrograde reaction is relatively lower order than prograde reaction rate. Okay, so and apart from that, partial metamorphism, rocks undergoing incomplete metamorphism may also retain zones of higher grade assemblage surrounded by lower grade. So these are the certain circumstances when they can coexist, lower and higher grade. Further, another point is polymetamorphism. Multiple metamorphic events with different PT, pressure, temperature, history can superimpose contrasting phases within the same area. So, metamorphic history also can play a role, but apart from that, structural deformation related things. And third parameter is fluid and metasomatism. Again, fluid rich lower grade facies are often found in zones where fluids lower the metamorphic temperature or facilitated retrogression. As I have told, fluid cause hydration. Hydration means it is retrogression. Okay, so suddenly due to fluid addition, higher grade facies may be converted partially into lower grade. Similarly, fluid depleted zones, granulite facies rocks can often occur in areas where fluids are absent, preventing retrogression and retaining high grade assemblages. So these are the certain things. Apart from the thermal gradient, suddenly local heat source, intrusion of magmatic bodies can create steep thermal gradient, causing adjacent rock to experience varying pressure temperature condition. Then thermal overprint, local heating, and another very important thing is original compositional variability. Different rhodoliths may respond differently to identical pressure temperature condition, produce different metamorphic assemblages. For example, pellitic rocks may form granulite facies, and same condition mafic rocks may form amphibolite facies. Sometimes it is not very much usual thing, but sometimes this is also can be possible. Facies means mineral assemblage. As I have told, that mineral assemblage is indicative of particular pressure temperature condition. So sometimes carbonate rich rocks may remain lower grade condition in spite of giving enough pressure temperature condition, which is in which most of the rocks become amphibolite. Likewise, but now if we see this area, Tanga area, graphite mineralization, this gray color graphitic zone is of course low to medium grade, and immediately adjacent area, both the side you can see granulite, although it is width is maximum 400 meters. So within 400-meter granulite, then amphibolite green cyst, and then again granulite. So granulite amphibolite green cyst transition is occurring within 400 meters and with certain sharp, more or less sharp broad contact. Sharp contact you can say, suddenly, not a gradational contact. And even if we drill within this low grade, some area patches of higher grade garnetiferous intervals also encountered. So what may be the reason? First of all, by seeing this, it is easily visualized there are certain faults. Okay, north-south faults that is related to east-west compression. Okay, so these north-south faults are often related to that orogeny. This is Mozambique orogeny related mobile belt. So east-west compression led to north-south fabric development, and that fabric, due to that open a very close isoclinal, tight isoclinal folding, causes foliation, axial planar foliation, which is dipping easterly. Thrust is also dipping easterly. So all the major fabrics dipping easterly here, and major strike is broadly north-south. So because of these kinds of thrust and folds, often they found to occur together. You can see this sketch here. For example, green cyst at the top, then amphibolite, then granulite, then other higher grade or basement complex here, lower one. But now if it is intensely folded and thrusted, what will happen? Within a short range they will be coexisting, they will be occurring together almost, because as per the Pimpel's rule, whatever found in the regional scale, fold and thrust belt exhibit similar features across regional local outcrop scale. So whatever found in regional scale, it will be replicated in outcrop scale as well. So that is the structural hierarchy of fold and thrust belts. First order structures in regional scale, same thing will be replicated in second order structures, local scale, even in third order outcrop scale, microscopic scale. See, folds can be forming synclinuria and declinuria. The same thing will be replicated in the form of tight to open isoclinal folds on limbs. And further, if we detail, see, parasitic folds, king bands will be observed. Folds also will be thrust sheet and imbricates nearby. In same thing in local scale, it will be like splays. Further detail, if you see outcrop, it will be observed slick and slide gouge. Similarly, regional slutty cleavage, zoned cleavage, spaced granulation cleavage. These are all the things are dependent upon the scale of observation. That's all. Shear zone also same thing happened. So similarly, if regionally green cyst, amphibolite, granulite facies form at different pressure temperature condition, but when that intense folding and thrusting take place, they can occur together sometimes. And apart from that, as I have mentioned already, tectonic juxtaposition is one of the possible role. Apart from that, polymetamorphism, localized metamorphic condition, and prograde and retrograde relationship, all are important. But since graphite, see, prograde retrograde relationship is happen when higher grade rocks may represent prograde metamorphism, while adjacent lower grade rock represent retrogradation due to addition of lateral fluid, infiltration or cooling. But high likelihood of getting these things is very less, because if that lower grade graphitic rocks underwent higher grade metamorphism, then how again when in returning back, graphite is not available in granulite phases. It would have been present in both in that case. So we can easily cut out this possibility. Now localized metamorphic condition, of course, variation in heat, pressure and fluid availability can create local pressure, temperature and environment. That is one reason. Another one is protolith. Since this is a stratified layer metamorphism, but this is meta sediment, sedimentary bedding, and sediments protolith were different in nature. So whenever they have encountered graphite rich or carbonaceous material rich protolith, they within same pressure temperature condition, due to porosity permeability variation, at some places it become amphibolite to higher green cyst, at places it become granulitic. So all the three factors may be substantiated. One is tectonic juxtaposition, then differential metamorphism and lithological variation. Because of these three factors, the area shows juxtaposition of different metamorphic facies and metamorphic grade assemblages.